How to analyze circuits in time domain with TINACloud. In this tutorial video, we will demonstrate and compare the tools available in TINACloud for analyzing circuits in time domain. In TINACloud, you can analyze circuits in time domain employing two different tools: transient analysis from the analysis menu of TINACloud, simulated virtual oscilloscope from the TNM menu of TINACloud. Transient analysis. The transient analysis calculates the time response of circuits and presents the results as diagrams or text. First, let's analyze this circuit with transient analysis through the following steps. Load the circuit coalpits.tsc from the examples folder of TINACloud. The transient diagram is already inserted into the circuit. Delete it before simulation. To delete the diagram, first click the diagram and then click the red X delete icon on the toolbar, or press the delete key on the keyboard. Delete the additional text in the same way. Note that the program automatically saves the changes into this file while you are editing. Select Transient from the Analysis menu of TINACloud. The Run Transient Analysis dialog appears. You have to set the start display and end display parameters of the analysis here. The default value of start display is 0. If you change it, the analysis will still start at t=0. However, the result will only be displayed from the start display time point. End display is the duration of the analysis. For coalpits.tsc, it is preset, but for new circuits, you have to estimate it based on circuit operation. It's also important to select an option related to the start condition. For oscillators, like our circuit, the 0 initial values option applies. Note that most oscillator circuits will not work in simulation without this setting. For amplifier and many other circuits, you should use the default Calculate Operating Point option. To get the diagram, you just have to press the Run button. The result of the transient analysis then appears. You can refine the diagram in several ways. Here are a few. Zoom into any part of the diagram. Run cursors on the curves of the diagram. Calculate the frequency of the oscillation. Note that frequency and slope under the View menu must be enabled. Mark a period of the signal with the cursors. You can also find the local or global minimum or maximum by clicking the actual value field of a curve. You can also enter values to set the cursors more precisely. You can add labels to the curves showing the name of the related output on the circuit. Separate the curves or collect them in one diagram. You can insert the diagram into the schematics and save them together. Close the diagram window. Note that it remains available in the program. Select Insert Diagram from the Insert menu denoted by a green plus sign. Press the Insert button. The diagram will appear attached to your cursor. Position it, and then add it to the circuit diagram by pressing the left button of the mouse. Virtual oscilloscope. Now let's learn to operate the simulated virtual oscilloscope. In practice, we very often use an oscilloscope to measure, analyze, and debug circuits in the time domain. So it seems obvious that a simulated oscilloscope can be used in circuit simulation as well. However, there are a few important differences between the two that you must know about. Even if you analyze the circuits in a computer with a simulated oscilloscope, it is still simulation. You should not consider it as measurement unless you use real-time data acquisition for obtaining the data. The simulated oscilloscope is very useful when you want to adjust some component values of small circuits and want to see the effect of the changes immediately in order to fine-tune your circuit. For large and complex circuits, the simulation may take longer, minutes and even hours. In such cases, it is inconvenient to use the oscilloscope controls, as unlike in the case of real measurements, you cannot see the waveform and the effect of the changes immediately. In these cases, it is better to use the transient analysis from the analysis menu of TINACloud, which creates a diagram when the simulation is finished. Now let's analyze our Colpitts oscillator circuit with the simulated oscilloscope of TINACloud. Invoke the oscilloscope from the TNM menu. Press the Run button. The Out1 signal appears. Use the controls to make the curve bigger and more detailed. By default, the oscilloscope is in the auto, i.e. free running mode. To get a steady state image, you should enable triggering as follows. Set the trigger mode to normal. Set the trigger source to Out1. Set the trigger level to 300 millivolts. Consequently, the waveform is stabilized. With the controls of the oscilloscope, you can make a lot of changes on the displayed waveform. Here are a few. By default, on the oscilloscope's rising edge, triggering is used. So the display starts when the signal rises above the trigger level. You can also set this to falling edge triggering, where the display starts when the signal falls below the trigger level. You can also bring in the Vout signal by selecting Vout under Channel. Let's have the same vertical settings for Vout as for Out1. Finally, you can export the display into a diagram by pressing the Export to Diagram button under Data. Note, make sure the oscilloscope is not running. For small circuits, you can also use the simulated oscilloscope to fine-tune your circuits. For example, you must have observed that in our oscillator, while the Out1 signal is sinusoidal, the Vout signal is quite distorted. Let's fine-tune the circuit by changing the R resistor so that both Out1 and Vout are sinusoidal. Double-click the resistor R on the schematic. Now you can change the value of the resistor with the up and down arrows at the right-hand side of the dialog box and watch the waveforms on the oscilloscope. You can also set the step size. Change it to 500 ohms. Raise the resistance to 5K in 500 ohms steps until both signals become sinusoidal. Transient recording. You can still get the full picture if you set the trigger mode parameter to single shot. In this case, the oscilloscope will display the curves only once, similar to how it is done in the transient analysis. In order to compare with the transient analysis result you already have, reset R to its original 1K value. Now select Single under Mode. You must also set the horizontal time division settings accordingly. And the trigger level to 0. Press the Run button. You will see the same signal on the oscilloscope as provided by the previous transient analysis. In conclusion, you can get the same results using transient analysis and simulated virtual oscilloscope in TINACloud. The virtual oscilloscope is closer to practical measurements and can be very well used for interactive fine-tuning of circuits, while the transient analysis is simpler to set up, and it is the only tool for analyzing large circuits. For more information, visit our website, www.tinacloud.com. Visit our YouTube channel, www.youtube.com/user/Tina Design Suite.